I'm now going to finish this lecture on the dual group by introducing some properties of the dual group and also some examples. All right, so first of all, I want to show the following. So it's kind of motivated from the Fourier transform of the classical harmonic analysis. If you think about all these e to the int, they kind of form a orthonormal basis of the L2 of the unit circle. So something similar actually happens in the dual group here. So if G is, let's say, locally compact abelian, and let's just assume for now that G is compact. Okay, so let's assume G is compact. For example, if when G is the unit circle and so on. And you can always normalize your normalize your left Haar measure so that it's a probability measure. Okay, so let's assume the Haar measure is a probability measure. Okay, so then what you can show that your G hat is going to be inside L2, and in fact they're going to be an also normal set. Okay, so it's an also normal set. Okay. Also, normal essentially means their integral against each other are going to be 0 unless they're equal, and the norm of each one of them is going to be 1. Okay, the norm being 1 is kind of trivial from your mu is a probability measure, and your character is mapping your G to the unit circle. So let's just prove that they're orthogonal to each other. Okay, so let's let any psi and eta inside G hat. Okay, let's pick 2 of them. And let's suppose they're different. So by different, it means they have to differ somewhere. Okay, so there is some, say, x0 inside G, so that psi of x0 is different from eta of x0. Okay, so they have to differ somewhere. All right, so now let's consider the integral of their psi times theta conjugate d mu. Okay, so you do the inner product of these two. And what you have is that this is essentially just, if I write out the integral, you have a psi x, and we talk about the conjugate of the psi, conjugate of a character is essentially just the character evaluate at the inverse map, or it's essentially the inverse of this character. Okay, so this is just eta x inverse, okay, d mu of x. All right, so now what you can do is that you use the left translation, and you say, well, how about let's translate my x by the x0, okay? So I translate x to x0, say x0 inverse of x, okay? So now this is become the psi of x0 inverse of x, and then I times the eta of the x0 inverse of x, the whole thing to the inverse. So I have the x inverse, and then I have x0, the mu of x. Okay, the order doesn't really matter here because everything is abelian. But what you can now do is that you can pull out a copy of because your psi and eta, they're multiplicative, you can pull out a copy of the psi x0 inverse and eta of x0. So let's pull them out. So you have an eta of x0, and then multiply by psi of x0 inverse. Okay, psi is a homomorphism, so psi of x0 inverse is the psi x0, the whole thing inverse. And the rest you keep it in the integral. Okay, so the rest you have a psi of x, you have a eta of x inverse, you have a d mu of x. All right. And you notice, well, you're basically doing the same thing here. So whatever you start with, you have it again here. But you now just pull out, magically have a scalar outside. So, well, hopefully the scalar is 1, but it turns out it's not. Okay, because when you first picked the x0, you picked so that these two things are different. So eta x0, psi x0 inverse is never equals to 1. So this is not 1 by your choice. And so if you have something that's equals to some not equal to 1 times itself, it just means that something has to be 0. Okay, so in other words, you just prove that this integral psi times theta bar is going to be equal to 0. Okay, so basically we showed it's an orthonormal set. All right, so in particular, let's do a quick corollary. So in fact, if you just consider the constant one function, if you integrate everything against the constant one function, well, because things are also normal, so you should be able to get zero. Okay, so it's a corollary for every psi inside the G hat, and as long as your psi is not the identity one, which we use in notation phi of E, okay, then the integral of the psi d mu, that's just always going to be equal to zero. Okay. One way to think about this as an analog of the integral of e to the in theta is always equal to zero, unless you're just integrating when n is equal to zero. Okay, you're integrating the constant one. All right. So that's kind of the analog for these dual groups. All right. The next thing I want to prove is some kind of duality between this group and dual group. Okay, we're going to see this kind of duality later on in the puncturing eigen duality. But here, let's do the following. So suppose my G has a discrete topology. So if G is discrete, that's going to prove, well, that will imply that G hat, the dual group, is going to be compact. Okay. And conversely, if my G itself is compact, then turns out the dual group, okay, this G hat is going to be discrete, okay? So you kind of have this duality, okay? So later on, when we prove the puncturing eigen duality, you can essentially say, well, this is essentially if and only if, because the G double dual is G itself, okay? But anyways, right now we only have these one directions. All right, so let's give it a proof. Well, the first one is kind of the consequence from the Gelfand theory. So if G is discrete, then when we talk about the L1 as a Banach algebra, we talk about when you have a discrete group, then the constant, the characteristic function at the identity of G, that's going to be in L1, and that's going to act as the unit of your Banach algebra. Okay, so L1 of G is going to be unitole. And because it's unitole, we prove when we talk about the Gelfand theory, when you have a Banach algebra that's unitole, then the maximal ideal space is going to be compact. Okay, so in that case, I have the maximum ideal space L1 of G that's going to be compact, and that's maximal ideal space we showed is essentially just the dual group. So the dual group is compact. Okay, so that's the easier one. So on the other hand, suppose I start with a compact set, so G is compact. Well, when G is compact, then the constant one function now becomes an L1 of G, okay? Because you have a compact set, the measure of your G has to be finite. You can even take a probability measure. So let's let one, this bold one, to be the constant one function. Okay, so that's going to be in L1 of G. That's not the unit. Okay, so it's not the unit. When you convolute with other stuff, it doesn't preserve it. But it's just a function inside the L1 of G. All right, so now I have, if I consider what happens in the weak star topology on the G hat, if I consider all those functions where, let's say, f inside L infinity, where the integral against this constant one function f d mu is going to be greater than a half, okay? So suppose, let's say the set is U, okay? That's going to be an open set in the weak star topology, okay? You're testing against this one L1 function. All right, so now let's consider the identity character. Consider, let's say, phi e, the identity character inside G hat. All right, so if you have every phi inside your G hat where this phi is not identity or not phi of E, okay, then from the corollary we just showed, the integral of phi d mu, that's going to be equal to 0, okay? Well, because when you integrate this phi d mu, that's equal to 0, so in other words, the integral of the constant one function as a one function multiplied by your phi d mu, that's going to be 0. 0 certainly less than a half. So what you showed is that this phi is not inside this open set U here. Okay, so you pick the weak star opens at U, everything, as long as you have a non-identity in your G hat that's not inside U. Well, also what happened? Well, that just implies the identity in G hat itself. Well, it's going to be an open set inside the G hat in a relative topology. Okay, so that just implies that if you consider the singleton phi v, okay, inside G hat, okay, that's open. Okay. And when your singleton is open, the topology is going to be discrete. Okay, so that proves the G hat is going to be discrete. All right. All right, so that finish this kind of duality between compactness and discreteness of this group and this dual. Okay. Well, the next proposition I want to show is kind of an easy one. So suppose I have a bunch of GI, so G1 up to Gn locally compact Hausdorff abelian. Okay. As you recall, one way of constructing a abelian group is just taking the direct product. So let's take the direct product, eigen from 1 to n of these GI. You can, well, when you take a direct product, a abelian group is still abelian. The topology is, well, product topology is again locally compact Hausdorff. So you can talk about this dual group. It's going to be the same as the product of the dual group. Okay, so you always have these two are the same. All right, the proof is kind of trivial. So first of all, if you have any phi, let's say call it phi 1 up to phi n inside the product of these dual groups, so Gi dual, I go from 1 to n. In other words, each of these phi I come from one of the dual groups. Okay. So you can define a, let's say, phi tilde of G1 up to Gn. Let's essentially just say that's product of phi I of Gi, okay? I going from 1 to n. You can convince yourself this is indeed a character, okay? So this is a character on the product of these Gi, okay? So in other words, you take any element on the right-hand side, you can just take their product basically, and you get something, a character on the left. And you do the same thing conversely. So let's say conversely, you take phi is inside the product of Gi, I go from 1 to n, their dual group. And what you can do is you just fix and coordinate, and you can define a character on the corresponding coordinate. Okay, so you let, let's say phi tilde here, so consistent. So you let phi I of the Gi to be kind of the standard trick of embedding your group inside the product. So you do the phi tilde of you put identity on everything except the ith coordinate. Okay, so this is the ith coordinate. You put a G here, Gi there, and you just let everything else to be the identity. Okay, that's how you embed Gi inside this product anyways. All right, so you, based on that, you can convince yourself this, if you evaluate phi tilde of G1 up to Gn, okay, that's going to be equal to the product of this phi I Gi, okay, so this phi, this map where we have phi up to phi tilde, you can go both ways, okay, so essentially these two are going to be the same. All right, so let's finish our some basic properties of the dual group.